Hello and welcome to Disruptive Now, a podcast devoted to having disruptive technology in a readily available and easy to digest format. High caliber researchers have the opportunity to inform wider audiences about their research in an understandable way. Disruptive Now acts as a centralized network of innovation. In this episode, we invited Dr. Brendan Smith, who is an expert in computational chemistry, and we'll be discussing how simulations can help drive research for 2D materials. Dr. Smith, welcome.
Hey, how's it going?
Fantastic. Thank you very much for asking. So tell us a little bit about your love for computational chemistry.
I graduated with my PhD in chemistry from SUNY Buffalo in the spring of 2021. Worked at a computational chemistry startup as a software developer contractor for about 3 months. And then I transitioned into a full-time role at the company I'm at now called Kubrick, C-U-B-R-C Inc., located out of Buffalo. And I worked there as a software engineer with a focus on machine learning. I got my PhD in computational chemistry. I wanted to transition into industry because, I like academics, but I felt like a lot of the innovation was happening in industry. Actually, a lot of, at least on the material science side, a lot of the programs that people are using were, I don't know, it has a feel of like the 90s and 80s. And this is my old boss at the computational chemistry startup would say that there's more technology in your phone than there is in the programs people are using for computational chemistry. So a lot of the innovation was happening in industry, and I wanted to switch from sort of the academic track to the industry track. So I ended up getting a job as a data scientist, software engineer, machine learning, data scientist kind of role.
Thank you for that. As far as I know, computational chemistry is where we describe atoms and electrons using mathematical parameters such as matrices, and then we use the science that we've learned through experimentation to try and predict how these materials are going to act electrically. There's different scopes, so you have a very computationally intensive method, so you try and account for a lot of the atoms, but there's other ones where you don't use a lot of computational power and you kind of have it as like a big shell instead of lots of little things.
Yeah, so there's definitely different spectrums. We would call these levels of theory. You can go all the way to like the highest level of theory. You can get as fine grained or coarse grained as you want. It all depends on really the size of the system and the level of detail you want. For material science, I think we actually have to stay a little bit more coarse grained because the systems we use are much larger. Versus if you're working with like small molecules, low numbers of degrees of freedom, you can actually solve the Schrodinger equation with sufficiently high accuracy.
An example may be two hydrogen atoms interacting. To model that, you have to have a single proton and a single electron per atom, and that might be modeled quite easily. However, if you describe a solid lattice, there could be thousands upon millions of atoms interacting, which could be quite computationally intensive.
Yes.
Nice. So discussing computational chemistry, why is it important to material scientists?
I think there's like two main directions. I think it would be important to material scientists for sort of another tool you can use for material characterization. And it would also be of interest to material scientists for the process of material discovery. For that first one, for material characterization, I think computational chemistry methods can help you obtain predictions of material properties, such as electronic structure, excitation spectrum, geometries, and also dynamical properties, such as like what I was working on in my PhD, like hot electron dynamics, hot hole dynamics. So this would be like silicon slab gets some laser beam on it, photoexcite electrons, photoexcite holes, and then these interact with the crystal phonons and relax. And that actually controls like the performance of photoabsorbing layers and solar cells. For materials discovery, I think the idea is that you can leverage data provided by computational chemistry methods and experiments to predict new materials. And so I think in any case, computational chemistry is an invaluable part of material science research nowadays.
So you kind of predict the future, and then experimental scientists can go outside there and kind of prove you right or wrong, or it can establish like a database of, for example, 2D materials to go out there and isolate.
Exactly. And there's also the sort of that's like I think the role it's transitioning into, or more of like a support for experiments. So there might be some experiments going on and they just want a little bit more color into a certain process. So they might like have simulations to aid them. But it's not acting in a discovery fashion. It's acting as a tool for further characterization or supporting evidence of a characterization.
Okay, so you can use computational chemistry whilst you're doing the experiments and post and pre. So it sounds like a pretty important topic. So how exactly do you find out or predict these things with computational chemistry?
Ultimately, you just solve the Schrodinger equation using computer programs. It's all about the level of detail you want. So it's really more of a question of accuracy.
So you solve the Schrodinger equation to get an energy of a group of particles, and then you assign that to an energy band diagram.
Yeah. So like for example, if you're interested in computing the ground state geometry of a material at a given temperature, in order to get the ground state geometry correct, you have to get the ground electronic state correct, and that involves correctly solving the Schrodinger equation.
That's awesome. So when we first connected, you showed me a system that you can use to design heterostructures, heterostructures being 2D crystals laid on each other. Can you go into a bit of detail in what you believe heterostructures are?
So I think heterostructures are sort of layered systems comprised of chemically different materials. I think the most important part of like once something becomes a heterostructure is when the interaction between the two component materials can't be ignored. So like once that interaction term becomes significant, then you have a heterostructure.
Okay, so you might consider graphene with MOS2 and then graphene with hexaboronitride. One may interact differently than the other, and that's kind of the threshold that you have to design heterostructures.
Yes.
Fantastic. So why are heterostructures important?
Really, they offer a way to obtain and control material properties. Just as you had mentioned, you might bring two different like 2D materials together to sort of do charge separation after photoexcitation. Whereas if you had like graphene on graphene, you would just, if you keep layering graphene on graphene, you would just get bulk graphite. But if you start layering different materials together, you would get, something very different from bulk graphite, for example.
I see. So yeah, the world works a lot on bulk properties, right? You have a big chunk of atoms and they all kind of act the same. But with heterostructures, you can kind of manipulate how they're going to behave on like a atomic scale, essentially. And so you can have things that are separated by a few nanometers act completely different than each other.
Yes.
So what comes next for heterostructures?
We're still in the exploration and development phase. For some material interfaces, like probably these 2D ones like graphene, hexagonal boron nitride, molybdenum sulfide, I think we may be a little bit more downstream and concerned with like commercial production, potentially serving end markets, although I don't know too much about that. I think for the most part, given like the large possible combinations of heterostructures you can create, I think really we're going to be in this, like still exploring this space of possible heterostructures for quite some time. And I think materials discovery is going to be a big part of this sort of exploration.
I see. So it's kind of like there's so many options out there because the amount of 2D crystals is wide, and we don't really want to put any money on any horse before we fully understand the scope of what we might be getting into.
Right. And it gets even larger when you consider like, zero dimensional structures, like layers of quantum dots on
Mm,
things as well. And also these organic, inorganic crystals, 2D, 3D perovskites that were hot, at least when I was finishing my PhD. So that space of exploration is very large. I think we're going to be there for quite some time.
yeah, so you talked a little bit about the commercial landscape there and the industries that this might be applicable to. Primarily, we've been talking about, the charge separation, so photovoltaic cells and things really to do with electronics and microelectronics or nanoelectronics. Could you envision heterostructures having an impact on any other field?
I think I had saw some stuff about like separation of chemicals, maybe in like more on like analytical chemistry side. Also, I think photocatalysis, there's some applications there, but I don't know too deeply about those. But I remember like just kind of reading that stuff when I was going through my at the later parts of my PhD.
I love that. Yeah. I believe that the ability to manipulate materials on the atomic scale, like the potential is limitless, and computational chemistry really helps us guide on where to go next.
Yeah, definitely.
Fantastic. Well, thank you very much for your time, Dr. Brendan Smith.
Thank you so much for having me. I appreciate it.
Great to get a professional viewpoint on the field at the moment because computational chemistry is something very close to my heart, and seeing the innovations it's going to create and more people getting involved is very inspirational. Alright, that was Dr. Brendan Smith of Kubrick, and his contact details are in the episode description. All that remains to be said is you can find more information on all types of social media, and you can contact NanoRD at www.nanord.ca. Keep feeding your genius side with the nectar of science.